Greetings to all of you. Welcome back. Today I come with a very important topic from organic chemistry, that is the isomerism. First, define isomers. Different compounds having same molecular formula but different physical and or chemical properties. Different physical or chemical properties, that is known as isomer. And this phenomenon of existence of different compounds having same molecular formula but different physical or chemical properties is known as isomerism. Now, isomerism is further classified as constitutional or structural isomerism or stereoisomerism. Now, structural or constitutional isomerism, as the name suggests, means it has different connectivity, constitution, different connectivity, different kind of atoms, different type of groups attached to each other. Means it can be defined as different molecules having same molecular formula but different structural arrangements. Different structural arrangements, and they are classified as chain, positional isomerism, functional isomerism, ring chain isomerism, metamerism, tautomerism, and pseudotropism. Second part is stereoisomerism. Stereoisomerism means these are the isomers which have same molecular formula, same structural arrangement. In this case, different molecules have same molecular formula, same structural arrangements, but they have different arrangement in space. That is called spatial arrangement. They differ in their spatial arrangement. Stereoisomerism is further classified as conformational isomerism and configurational. Now, what is the basic difference between these two terms? Conformational means which have free rotation. There is a carbon-carbon single bond and free rotation is possible. Means these forms are interconvertible. Means one form can be converted into another at room temperature. And there is no need of breaking of bonds or formation of bond. Without breaking or formation of bonds, one form can be converted into another. There are infinite number of conformational isomers. Now come to configurational. Configurational isomers are those which have same structure, molecular formula, but different arrangements, and they cannot be converted from one form to another without breaking or formation of bonds. And they are further classified as geometrical, that is also called cis-trans isomerism, and optical isomerism or enantiomerism. So this is the overall view of isomerism. So what are structural or constitutional isomers? Which have same molecular formula but different structural arrangements. So first one is chain isomerism. So as the name suggests, chain isomerism means these are the isomers having same molecular formula, same functional group, but different number of atoms in main chain. Means they have different word root. Keep in mind, they have different word root. For example, butane. So minimum number of carbon atoms required for chain isomerism are 4, except in alkyne. For example, this is normal butane and this one is, isobutane. There is a change in word root but same number of carbon atom. And one more thing you have to keep in mind, that isomers should have same degree of unsaturation. Molecules should have same degree of unsaturation. So degree of unsaturation should be same for isomers, and degree of unsaturation is counted by calculating number of pi bonds and number of rings. One pi bond, 1 degree of unsaturation, one ring, 1 degree of unsaturation. For example, in this case, there is no pi bond, no ring. So what is degree of unsaturation? 0. Its degree of unsaturation is 0. Come to next part. It is but 1 in, and this one is 2-methyl prop 1-ene, or simply propene. So they are chain isomers and have same degree of unsaturation, 1 pi bond. Keep in mind this thing. Now, next example. This is second example. Come to pentane, C5H12. In pentane, all the 5 carbons in straight line, 4 carbon in straight line and 1 carbon. If there is 1 methyl as a substituent, that is called iso. If there are 2 methyl as a substituent, that is called neo. So it is normal pentane, isopentane, neopentane. Normal pentane, isopentane and neopentane. So this is pentane. What about this? 2-methyl butane and 2,2-dimethyl propane. Chain isomers, because there is a change in word root, pentane, butane, propane, and carbon atoms are same. Degree of unsaturation is same. So minimum number of carbon required by a molecule or compound are 4 to show chain isomers, except in alkyne, because in case of alkyne we need at least 5 carbons. So these are chain isomers. Pent 1-ine, 3-methyl, but 1-ine. They are chain isomers. But if we have butane with 4 carbons, we cannot have chain isomer of but 1-ine. So keep in mind, except alkyne, all other molecules need 4 carbons to show chain isomers. Right? Second part of structural or constitutional isomerism is positional isomerism or position isomerism. So in position isomerism, same molecular formula, same chain length, same word root means on a different position of functional group or substituents. For example, if we have 1 chloropropane, 2 chloropropane. So both are chloropropanes. But first is 1 chloropropane, other is 2 chloropropane. So there is a change in position of chlorine. So they are under the heading of positional isomerism, and they are position isomers. One more example, but1-ene, but2-ene. Again, change in number or position of double bond. So they are again position isomers. They are position isomers. 1,2 dichlorobenzene, 1,3 dichlorobenzene, 1,4 dichlorobenzene. All are dichlorobenzene. But this is 1,2, this is 1,3, 1,4 dichlorobenzene. So they are also position isomers. One more example. This is 1,1 dichloroethane, and this is 1,2 dichloroethane. So they are again position isomers and studied under the heading of positional isomerism. Yes, one more thing. This is called, these positions, 1, 2 positions are called ortho. So this is also known as orthodichlorobenzene. 1,3 meta. So they are metadichlorobenzene, and 1,4 para. So they are also known as paradichlorobenzene. Same the case here. If both the substituents or functional groups are attached on the same carbon, that is called geminal. So these are geminal dichloride, and if they are attached at 1, 2, they are known as vicinal. So they are vicinal dichlorides. So this is about positional isomers or positional isomerism. Now could you calculate total number of isomers of hexane C6H40? So what do you do? First, there are 6 carbon, 1, 2, 3, 4, 5, 6. Then reduce 1, 5 carbons, 1 carbon left. Now this carbon is attached to only 1 carbon, so it is called primary carbon. Carbon attached to 2 carbons, secondary carbon. Carbon attached to again 2, secondary, primary. You have to look in between the extreme carbons, terminal carbon. In between the terminal carbon, these are secondary. Now tell me, how many types of secondary carbons are there? There are, yes, 2 types of secondary carbons. This secondary carbon attached to primary and secondary. This secondary carbon attached to secondary, and this one is also attached to primary, secondary. So these 2 are of same type, but it is of different type. So that means we can attach carbon at 2 different secondary carbons. So this is 1, or we can attach here. This is the case. Then come to reduce, and next 4. Now we left with how many carbons? 2, and carbon between the terminal carbons are secondary, and both are of same type, and we have left with 2 carbons. So either we attach both the carbon at the same place. So this is either attach this side or that side, remain same, or we can attach like this. Total isomers of C6H14 are 1, 2, 3, 4, 5. Not more than that. So total isomers are 5 for C6H14. So what is the relation between these isomers of C6H14? Hexane with pentane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, 2,3-dimethylbutane, they are chain isomers. 1, 2, 1, 3, 1, 4, 1, 5, all are chain isomers. But what about 2 and 3? 2-methylpentane, 3-methylpentane. Only position of methyl changes. They are position isomers because word root remains same, but position of methyl changes, so they are positional isomers. What about this? Again same. 4 and 5 again are positional isomers because this is dimethylbutane, but it is 2, it is 2, 3. So what is the relation of 2 and 4? Chain isomers. 2 and 5 chain isomers. 3 and 4 chain isomers. 3 and 5 chain isomers. And one more thing, if two compounds are chain isomers, they can never be position isomers and vice versa. So these are the pairs of positional isomers. Rest pairs are chain isomers. So functional isomerism, as the name suggests, different compounds having same molecular formula but different type of functional groups. They have different types of functional groups. For example, this is aldehyde, CHO group, and this is known as ketone. This is propanol and propanone. Same number of carbon atom, same degree of unsaturation, same molecular formula, but different functional groups. So this is, that means aldehyde and ketones, they are functional isomers. Come to, what is this? Well known, it is ethanol, used for various purposes, have medicinal use, can be used for drinking purpose. This is ethanol, and this is, if O is between two carbons, that is called ether. So this is, its IUPAC name is methoxy methane or dimethyl ether, common name. Its common name is ethyl alcohol. So that means alcohol and ether are again functional isomers. Cyanide and isocyanate. Alkyl cyanide, alkyl isocyanate. Again functional isomers. Nitroalkanes and alkyl nitrite. Again, functional isomers. Different types of amines. This is primary amine, nitrogen attached to one alkyl group. Secondary amine, tertiary amine. They are again functional isomers. Primary, secondary and tertiary amine. Now acid and ester. Well known acid is acetic acid. Now acetic acid and this is ester. This is common name is acetic acid and IUPAC name is ethanoic acid. And what is its IUPAC name? O instead of H is attached to methyl. So keep in mind, alkyl group attached to O is always written on the front. Methyl, and how many carbons are there? 1. Methanoic acid ka H is removed, so it is methyl methanoate. Keep in mind, methyl methanoate. One more example. What is this? Propanoic acid. And what is the name of this compound? Methyl and ethanoate. And what about this? Yes, this is ethyl methanoate. So propanoic acid is functional isomer of these esters. Phenol, this is 4-methyl phenol, and this is benzyl alcohol. So benzyl alcohol and 4-methyl phenol, they are also functional isomers because it is one sort of alcohol and this is phenol. So phenol and alcohol are also functional isomers. This is all about functional isomers. Next is ring chain isomerism. So in a ring chain isomerism, one isomer has straight chain and other have cyclic structure. It is possible only if straight chain alkene, straight chain isomer has at least one pi bond. Because if there is no pi bond, there is no chance for the molecule to have same molecular formula with a ring. Because I already told you that isomers should have same degree of unsaturation. So example, suppose we have propene. So its cyclic ring isomer is cyclopropane. Cyclopropane and propene have same degree of unsaturation. It has one pi bond, it has one ring. That's why both have same degree of unsaturation. One is chain, other is ring. So this is called ring chain isomerism. Okay. Another example, if we have butane. Now what is the degree of unsaturation? 2. So one ring, one pi bond. So these are ring chain isomers of each other. Another example is provided by This is alkene-ol, and this is cyclic ether. So alkenol and cyclic ether are again ring chain isomers. But keep in mind, whenever you draw the structure, the degree of unsaturation should be same. Metamers, they are isomers having same molecular formula, but nature of alkyl groups attached to the polyvalent atom or functional group are different. Means alkyl groups attached to the polyvalent atoms are different. For example, in ether, so you know, ether means if O is in between two carbon atoms. See, distribution of alkyl groups. In one side there are two carbons, other side also two carbons. But if I write it like this, 1,3, nature of alkyl groups attached to the polyvalent atoms are different in these two, so they are metamers. Next example is hexane 2-on, hexane 3-on. So they are again, see, hexane 2-on, hexane 3-on. Now if these two are metamers as well as position isomers, because there is a change in position of functional group only, word root remains same, functional group remains same, only position of the functional group changes. So this example shows both type of isomerism, positional isomerism as well as metamerism. Another example is given by secondary amines. In secondary amines, two, 3, and if we write it one, 4, so alkyl groups attached to NH are different, so they are again metamers, right? So in metamers, difference lies in the nature of alkyl group attached to the polyvalent atom or functional group. And ether, secondary amine and ketone provide us example of metamers and metamerism. Thank you very much for watching this part 1 to 4 of structural isomerism. Keep watching. Next video I will explain tautomerism in detail. So keep waiting for the next video, and do like, subscribe and share my channel so that you will get notification of my next video and you will not miss my videos. God bless you all. Thank you.